This is exactly what happens inside a core backend architecture when millions of simultaneous requests hit a standard database. The system hits a sudden deadlock, response times skyrocket to over 12 seconds, and your entire application crashes. But the world's largest tech platforms handle this exact type of traffic surge without a single millisecond of downtime. The secret isn't just buying more expensive cloud compute. It's understanding how to decouple your data state using core computer science fundamentals. When Uber outgrew its early infrastructure, they realized that synchronous dependencies were actively killing their availability. Today, we are breaking down the exact event-driven strategy to scale your architecture smoothly. First, let's look at the foundational principle of modularity. Just like isolating application state using clean, object-oriented principles, we split our system into deeply decoupled microservices. Each service owns its domain entirely, meaning the billing service can never touch the passenger database directly. In enterprise software engineering, we enforce this boundary rigorously to keep services highly modular. But now, these isolated services need a way to communicate. If they call each other synchronously using basic HTTP requests, your system becomes incredibly fragile. If the billing tier encounters a network delay, the dispatch service stalls waiting for a response, causing a cascading failure throughout the entire cluster. To stop this domino effect, we drop a distributed event streaming platform right in the center. This is where we introduce a distributed message broker like Apache Kafka. This changes our entire paradigm from synchronous execution to asynchronous event driving. When a passenger requests a ride, the traffic passes through the API gateway and load balancer, hitting our Kafka cluster. The dispatch service doesn't wait around for a downstream confirmation code. It simply publishes an immutable event called ride requested straight to a specific topic partition and immediately frees up its threads to handle the next incoming connection. Look closely at how data is distributed here. By splitting our topic log into partition 0, partition 1, and partition 2, we achieve horizontal scalability. Each partition tracks its current state using sequential data markers called offsets. Because these partitions run independently, our downstream consumers, the billing service, the dispatch microservice, and the notification engine can process these data streams asynchronously and in parallel. If traffic spikes exponentially, we don't crash. The broker acts as an architectural shock absorber, holding the messages safely in the queue until the services compute them. Finally, the processed events flow directly down into our distributed data tier and vector database, ensuring our data layer matches the speed of our ingestion cluster. By applying basic principles of modularity and scaling them with event-driven message pipelines, a system goes from crashing under load to smoothly handling over 10 million requests per second. If you want to build resilient systems that stand up to real production-level engineering requirements, you need a firm grasp of these core architectural layouts. Hit the subscribe button to master advanced high-level design patterns every single week. Now, scaling your application logic using a message broker is only half the battle. If your underlying database layers aren't partitioned to match this asynchronous flow, your storage engines will still bottleneck under heavy read-write cycles. To see exactly how to solve that storage crisis using advanced database sharding and write-ahead logs, click on this breakdown right here.